Okay, so this circuit shows an equivalent circuit for a current amplifier. So Is is the source current or an input current that needs to be amplified. Its direction shows the direction of this current, and this current source has its internal resistance indicated by Rs, which is in shunt with this Is. Now the current amplifier has three components: R in, the current I naught right here, and resistance R out. And all these components are indicated by the shaded square shape as shown in the figure. Now the internal characteristics of the current amplifiers are such that it has input resistance R in, which is ideally 0. So if it is ideally 0, it can be represented by a short circuit, and the current that enters inside the current amplifier will be II right over here, and which will be nearly equal to what is being sourced inside the amplifier. There will be a little current, a minute amount of current that will flow through Rs, considering in a practical current source Rs is much larger than R in, or in other words, R in is much smaller than Rs. Then the II is approximately equal to Is, and that is what precisely as a designer we want. We want all of the sourced current to enter inside the amplifier, and that is II. If such condition is violated, for example R in is comparable to Rs, then II, which will not be equal to Is, rather it will be somewhat lesser or much lesser than the Is. Now once the II enters the current amplifier, II, remember, is approximately equal to Is, what is being sourced. So when this current II enters the current amplifier, it gets amplified with the current gain indicated by AI, and the output current or an amplified current I naught will be equal to gain times the input current II. So that's why we write I naught is equal to AI multiplied by II, and this current I naught is indicated by this special current source, which is called as dependent current source. It is also called as current controlled current source, CCCS, current controlled current source. It means the output current I naught is controlled by the input current II. Now you have an output current I naught which is to be delivered to the load that is connected to the amplifier, and it is indicated by RL, and that IL is the current that will flow through the load, and IL ideally should be equal to I naught, what was amplified. The whole current flowing through the load should be what is available at the output of an amplifier. So R out here represents an output resistance of an amplifier, and that should be ideally infinite. That should be very high, ideally infinite. So if it is infinite, it can be represented by an open circuit. It means no current, or the I naught which is being delivered by this current source and is going right here will not flow through R naught, rather it will get flown through RL, which is nothing but your IL. So IL in such case will be approximately equal to I naught. Okay, but you will still have, in a practical situation, you will have a finite value of R naught, so some current will flow through R out very low, because R out will be still be very high, so little current will flow through R out and rest of the current will flow through the load. So IL is approximately equal to I naught. So that is how you can explain the working of the current amplifier through its equivalent model. So remember, in current amplifier, input resistance is very low and output resistance is very high. An exercise for you would be to draw and explain the equivalent model for a voltage amplifier